Hey everyone, today we're going to wrap up our momentum unit by covering something called impulse, which is kind of the trickiest part of this whole topic, but we'll get through it. I think we'll be okay. So for starters, we're talking about momentum. That's the topic of this unit. And momentum, remember, is mass times velocity. It's kind of like the amount of motion that an object has. And today we're going to look at how you can change an object's momentum. In other words, like if it has no momentum, how could you give it some? Or if it has a lot of momentum, how could you take some away? So let's start with this. I sort of wrote out the notes ahead of time because if you've been watching my videos, you know I have a hard time writing on my screen lately. So let's start with this. In order to change momentum, this says change. In order to change an object's momentum, a force must act over some time. So basically objects won't change their momentum on their own. They would change momentum because something pushes it. Right? Like objects at rest don't move spontaneously or like randomly. They move because something pushes them and makes them go faster, or maybe slower. And if you change speed, you're changing momentums. So in order to change momentum, a force must act on it. So what we're going to do here with today's lesson is we're going to tie momentum into force, and we'll sort of bridge those two different things. And that's the goal here of the equations and the concepts that we're going to talk about today. So in order to change momentum, a force must act over some time. Now, we have a word for this change in momentum, and this is kind of a weird one. The word for the change in momentum is impulse. Impulse is just a special word we have for the change in momentum. That's all it means. It's kind of like a weird idea. So let's say you map out like an object, and it's got a bunch of starting momentums and a bunch of final momentums. Let's call them, I don't know, PI and then PF, a starting and a final momentum. And then we're going to figure out what the impulse might be. So let's say you have a starting momentum of 2. I don't know. So the object's moving already. It's got a momentum of 2 kilogram meter per second. And then you speed it up so that it now has a momentum of 5. Impulse means the change in momentum. How much did it change by? Well, if you went from 2 to 5, what did you change by? We always calculate change by subtracting. 5 minus 2 gives you a change of 3. So impulse is kind of just momentum, but really it's a change in momentum. So if you went from 8 down to 6, how much did you change by? Well, 8 down to 6, 8 minus 6, that's a change of 2. Impulse. Let's say you went from a momentum of 10, and let's say you came to a complete stop. You ended with a momentum of 0. How much did you change by? If you went from 10 down to 0, well, 10 minus 0 is 10. So it's kind of a weird idea, but it's just a word that means the change in momentum. So I'm going to use those interchangeably, like change in momentum and impulse. They both literally mean the same thing, so I'm going to use them to mean the same thing, essentially. So impulse means change in momentum. And how would you calculate it? What's the mathematical relationships we got here? So we've got a couple of different equations here, but basically this is sort of your primary equation here. The change in momentum, which remember is another word for impulse. The change in momentum, or impulse, is equal to force times time. Force times time. So to figure out how much an object's momentum changes by, you take the force that you're pushing it with, and you multiply it by the time that it got pushed for. If you push it for 10 seconds, the time would be 10 seconds. So now what we did here, I know it doesn't seem like that was important or significant, but what we did is we tied momentum, which is this separate thing. It's that mass times velocity that we covered in the previous week. We took this momentum and we're now relating it to a force and a time. So we connected more different variables, and that's what's important about this. I wrote triangle P. We've seen this triangle before. It's meant to be the Greek symbol delta, which represents a change in momentum. So delta P is the change in momentum. Remember P equals momentum. F net is the net force, which we've covered earlier in the year, and then T is the time. Now we can rearrange this a little bit so that we could not only solve for the change in momentum, but we can also solve for that net force. The net force, if that's what we were looking for, is change in momentum over time. And remember, that change in momentum, that's just another way of saying impulse over time. So sometimes I'll use the word change in momentum, sometimes I'll use the word impulse. A big thing that I'm going to be testing here, or looking for, is that you understand that impulse means change in momentum. Just different ways of saying the exact same thing. And that's it. That's our idea. So again, just to make this, and if I had to say it in like a couple of really simple terms, impulse means change in momentum. It's a special word we have for that. And we can use it to solve for the force, we can use the force to solve for the change in momentum, or impulse. If you need those equations, they are, as always, on the last page. We've got these two down here. The only thing I did not do is spell out the idea that impulse means change in momentum. That's the only thing I didn't do for you on the equation sheet. But other than that, they're all right there for you. So let's go up and try a couple of these. We'll do 18, 19, 20 together, and I'll have you try the rest on your own, but obviously I'll go over them just like I've been doing. So let's go. A car has a momentum of 10,000 kilogram meter per second, and it slows down until it has a momentum of 2,000 kilogram meter per second. What's the impulse acting on the car? Okay, so there's a couple of ways you can think about this. This topic is a little bit tricky. I gave you, what does impulse mean? Well, what it means is change in momentum. So we're solving for the change in momentum. And that's sort of the most important point here. And there's a couple ways to do that. You could try the equation, which is probably the simplest thing to do, right? It's that F net times T. But if you read this carefully, I don't think you know any of this information. You don't know the force. We don't know the time. So which means we really can't use this equation. So let's cross that out. It was a good try, just wasn't the correct thing to do for this problem. But remember, impulse means change in momentum. Alright, well, you used to have 10,000 momentum, and now you have 2,000 momentum. How could you figure out what it changed by? Well, if you go from 10 down to 2, anytime we want the change, we subtract. 10,000 momentum minus 2,000 momentum gives you, I think, 8,000. The unit is kilogram meter per second, but I'm not going too crazy with the units this year. And there we go. The change in momentum. That's what impulse means. It means the change in momentum. I'm going to say that a lot of times this video. Number 19. A baseball pitch has a momentum of 5.8 kilogram meter per second. The catcher stops the ball in 0.1 seconds. What force is applied to the glove? We're solving for force, it sounds like. So force is, the equation that's solved for force is, I'm looking at this one right here. The net force is equal to change in momentum over time. Okay, we're solving for that net force, so I'm just going to plug in for the momentum, or the change in momentum, and the time. Well, we've got a momentum of 5.8. If it stops, then the ending momentum is 0. You go from 5.8 down to 0, I think the change is 5.8. And divided by time, this happens really quickly, the act of catching a baseball, so it's not a lot of time. It's 0.1 seconds. 5.8 divided by 0.1, do that one carefully in your calculator. I think you'll get a value of 58 newtons. Cool, and that's a good answer for us. So this is the amount of force it takes to stop that baseball. And again, we connected momentum and force in order to do that, and that's kind of why we care about this. 20. Determine the change in momentum. Remember, that's just another word for impulse. When a 50 Newton force acts on an object for 3 seconds. So we're solving for that change in momentum. Let's look at our equations and see if there's something that'll help us out here. We've got a 50 Newton force for 3 seconds. Okay, change in momentum. This equation is solved for the change in momentum. F net times time. So let's try that. It says the force, it's a 50 Newton force, so I'm going to plug that in as the force. I said 3 seconds, so let's plug that in as the time. And you get 150 And the unit for this change in momentum, 50 times, we did newtons times seconds, and so your unit is actually newtons times seconds. So the answer is 150, and the unit is newtons times seconds. And there we go. So based on the force, we were able to figure out how much the momentum changes by. Okay, so those ones we did together. I'd like you to pause this video at this point and try numbers 21, 22, and 23 on your own. I'm going to go over them in a second, but just, again, pause the video, give them a shot. Alright, I hope you took that opportunity to try all these. I'm going to go over them now so you can check your work. In a traveling car, you have a momentum of 2,000 kilogram-meter per second. Your car crashes and comes to a stop. What is the impulse? Well, in order to answer that, let's figure out what impulse means. Impulse means change in momentum. So if you start with a momentum of, let's just call it P start, of 2,000, your car crashes come to a stop, which means that P at the end, or your final momentum, is 0. If you go from 2,000 down to 0, I think your change was 2,000. So the answer to this question is actually just 2,000 kilogram-meter per second. Great. B, if you hit the dashboard, you come to a stop in 0.01 seconds. Determine the force stopping you. Okay, now we're going to calculate force. So let's check our equations and see if we have one that would let us solve for force. And I think we do. I think it's the second one right here. F net equals delta P over T. So that's the one that I'm going to use. Now remember, delta P, that's change in momentum. Another word for change in momentum is impulse. And I think actually, that's exactly what we found, right? We found the impulse before. It was 2,000. So I'm going to plug that 2,000 in as the change in momentum. Kilogram-meter per second. Yeah, that's 2,000. Over a time of, well, I said 0.01 seconds. That sounds like a time. So 0.01 seconds. All right. 2,000 divided by 0.01 is 20,000 newtons of force. That's a lot of force that you experienced in this car crash. And the reason that you ended up with so much force is you changed your momentum by a whole bunch, right? 2,000. And you did it really, really quickly. 0.01 seconds is 1/100th of a second. So to stop you really fast, it takes a lot of force. And that's dangerous, getting hit by that much force, right? So let's see what would happen if we stretched out the time a little bit, which is exactly what an airbag does. When an airbag deploys, it takes that 0.01 seconds and stretches it out over a longer period of time. Let's say 0.2 seconds, which is, I think, 20 times larger. Let's plug in and see what we can do here. We're solving for the net force again. So we're solving for the same thing, actually. But it's a different amount of time, so it's the same impulse, 2,000 kilogram-meter per second. But now it's not 0.01 seconds, it's 0.2 seconds. Again, a lot longer time. And let's see what that does to the force. When you divide carefully, I got 10,000 newtons. Whoops, I made a mistake earlier, everyone. I'm sorry. The answer to this one was 200,000. I apologize for that. Okay, but for this one, you do get 10,000 newtons. Okay, compared to 200,000, this 10,000 newtons is a lot less force. So your airbag made this a lot safer for you, meaning like it took a lot less force to stop you, you won't get hurt as bad. In fact, this time is 20 times bigger, so the force is 20 times smaller. So if you can stretch out an impact, you can make it like nice and slow and sort of gentle, the less force you will experience. 22. A 2,000 kilogram car is traveling at 10 meters per second. How much momentum does the car have? So we're solving for momentum, which was P. Let's check our equations, which are all on the last page. I think this one's a good fit, because you know the mass and the velocity. So let's plug those in. Oops. Okay, the mass was 2,000 kilograms. The velocity is 10 meters per second, and I think you get 20,000, kilogram meter per second. 20,000. Cool. Alright, let's say the car slows down. Now how much momentum does it have? Well, I'm asking for the same thing, so let's use the same equation, right? Why mess with something that worked for us? P equals mv. It's the same car, so I would imagine it has the same amount of mass, right? The car didn't magically shrink or anything. But it does have a different speed now. So instead of 10 meters per second, like in part A, I'm going to plug in 3 meters per second. And I think 2,000 times 3 is 6,000 kilogram meter per second. So this kind of makes sense, these two answers. The car was moving fast and had 20,000 momentum. Now the car's moving slow and only has 6,000. What is the impulse that acted on the car? Well, what does impulse mean? Impulse means change in momentum. Let's think about how we can calculate that change. We used to have 20,000 momentum. Now we have 6,000. What did it change by? Well, I think we can find that by subtracting. 20,000 minus 6,000 is a change of 14,000 kilogram meter per second. The change in momentum. So let's now calculate how much force was experienced by the car. It took 5 seconds to slow down. What's the net force on the car? Okay, so we're solving for the net force, right? Let's see if we can find an equation with net force in it. So let's go down to our equations. I think this one's a good fit. Net force equals change in momentum over time. Especially since we just found the change in momentum, which remember is impulse. So impulse means change in momentum. They mean the same thing. Equals 14,000 kilogram meter per second. All over, I think the time was 5 seconds. Alright, 14,000 divided by 5, if I did my math correct, is 2,800 newtons. The force experienced by the car. And again, to just kind of illustrate why we care about this, we took sort of these unrelated pieces of information. We took like a velocity and turned it into a momentum and turned it into a force. So we were able to connect these things that like don't initially appear very connected using this idea of impulse. Last up, a 0.15 kilogram egg comes to rest when a 30 Newton force acts on it for 0.15 seconds. What is the impulse acting on the egg? Remember, impulse is another word for change in momentum. That's what it means. And if you remember that, that's the hard part. Because let's look at the equations and find one for change in momentum. I think this one's a good fit right here. Delta P equals F times T. Because it's an equation for the change in momentum, which is what impulse means. Oops. F net times time. Okay, the force was 30 newtons, a 30 Newton force, so we're going to plug that in there. And then the time, right, time is measured in seconds, so it must be this 0.15. Alright, 30 times 0.15, do that math carefully in your head. I got 4.5, and the unit is newtons times seconds, because that's the math that we did. We did newtons times seconds. There we go. So impulse, kind of tricky, but you do have a worksheet on this that's going to be due on Friday. If you have trouble with it, email me with questions about it or come to my office hours. But try not to leave it to the last minute, because I do think this is one of the trickier topics that we cover in the whole course. So.